All right, today we are going to begin our series of lectures on second order transient analysis. We are going to specifically be looking at today parallel RLC circuits. So let's consider the following circuit. Gotta make sure I'm drawing my switch correctly. So I have the following circuit in which I have a resistor, capacitor, and inductor all connected in parallel, and they are connected to some current source, right? So at all time less than t is equal to 0, our circuit would be at DC steady state because we have a DC source connected to this network. And our inductor is going to have some amount of energy stored in it because all of that current IS will be flowing through the inductor, right? If this is a DC circuit, the inductor looks like a short circuit, the capacitor looks like an open circuit. So all of the current flows through the inductor, shorting out the resistor and effectively shorting out the open circuit of the capacitor, right? So there's energy stored. Now, when that switch moves from position B to position A, the current source is removed from the RLC circuit. And so what's going to happen is that inductor is going to transfer all of its energy between the resistor and the capacitor, and they're just going to pass energy back and forth until the resistor eventually converts all of this energy initially stored by the inductor into heat, because that's what resistors do. So our goal today is to develop the governing equations for how this transfer of energy occurs by figuring out what the voltage and current in all of the different elements are. So I'm going to start by saying that I have some common voltage V of t across all of those three elements in parallel. And I'm going to define my element currents as IR of t, IL of t, and IC of t. So during the transient condition, so that means after the switch has changed states, I can say that I do KCL at my top node. I get IR of t plus IL of t plus IC of t is equal to 0. I can express all three of those component currents in terms of that common voltage V of t, right? So for instance, IR of t looks like 1 over R times V of t from Ohm's law. Let's see, the voltage drop over an inductor is going to be, I'm trying to remember if this is the derivative-based relationship or the integral-based relationship, because I haven't done this in 3 months. I think it's the integral. Yeah. 1 over L integral from T naught to T of V of x dx, where x is just a dummy variable for time. And I cannot forget that I also have to include my initial condition, which would be IL at T naught. And then lastly over here, I have the current flowing through a capacitor is equal to the capacitance times the derivative of the voltage. This expression is what's known as an integro differential equation. You guys probably haven't had, or not all of you have had Math 245 yet, so you may not know how to solve these. So because I'm an electrical engineer, I'm going to cheat a little bit. And I'm going to simplify this thing greatly by just taking the derivative of both sides. So I'm going to get rid of my integral and come up with a second order differential equation that will be much easier to solve. So if I take the derivative, what I'm left with, I'm going to reorganize this guy a little bit. So I'm going to have C times the second derivative of the voltage plus 1 over R times the first derivative of the voltage plus, so when I take the derivative of the integral, I just wind up with 1 over L times the voltage expression itself. And when I take the derivative of that initial condition, which is just a constant value, it goes to 0. And I'm left with this guy. I'm going to make one more slight adjustment. I'm going to make the coefficient of my second derivative term 1. So I'm going to divide everything through by C, which leaves me with the second derivative of the voltage plus 1 over RC times the first derivative of the voltage plus 1 over LC times the voltage itself. So we now need to come up with an expression or a guess as to how the voltage is going to behave. So based on our prior experience of looking at RL and RC circuits and noticing that they had an exponential decay, I'm going to make that guess as well. So my guess is that the solution of this second order differential equation is going to be something of the form V of t is equal to A e to the st. So I have some coefficient that I'm going to need to figure out, and I have some natural frequency, which is what S is, that I'm also going to have to figure out. So if I substitute in my guess value, what I'm left with is the second derivative. So what's the second derivative of this guy? Yep, S squared AE to the ST plus 1 over RC times the first derivative, which is just S AE to the ST plus 1 over LC times the voltage expression itself, AE to the ST is equal to 0. And I'm going to rearrange this guy ever so slightly as well. So everything has a common factor of A, so I'm going to move that to one side. Then I have S squared plus 1 over RC times S plus 1 over LC, and everything has a common factor of e to the st as well. So my goal here is to figure out what makes this expression go to 0. So let's first look at that coefficient A. So if A is equal to 0, then this thing is 0. But that is a simple solution because it sets everything to 0. So effectively what it means is if I never had any energy stored in my system, the voltage by definition will always be 0. So that's correct, but it doesn't really help us figure out how energy is transferred because it assumes that there was never energy in the system to begin with. E to the st can decay towards 0 for particular values of S, but it will never be exactly 0. So instead, we're going to have to look at this guy here in the middle, which is called the characteristic equation for our system. So we need to figure out what values of S make this expression 0. Well, if we look at the equation that I have in brackets there, we can see that it is a simple quadratic, right? Where we have A is equal to 1, B is equal to 1 over RC, and C is equal to 1 over LC. So using the quadratic equation, we could say that we are going to have two solutions. S1 will be negative B, so that's negative 1 over RC plus the square root of B squared, so that's 1 over RC squared, minus 4 times A, which is 1, times C, so that's going to be 1 over LC. And I'm going to divide this guy by 2A, which is 2. And so what I'm going to do now is I'm going to distribute that factor of 2 that's in my denominator to make this guy look a little less funky. So I'm going to have negative 1 over twice RC plus square root of 1 over twice RC quantity squared minus the square root of 1 over LC quantity squared. All I've done in this step is just move that 2 from the denominator into the denominator of the numerator, if that makes any sense. And I also split my 1 over LC term up into the square of the square root of 1 over LC. I'm doing that because I'm going to define 2 new characteristic parameters of this system, okay? So alpha will be defined as 1 over twice RC. Alpha is what's known as the Neper frequency. It has units of Nepers, which is a dimensionless quantity per second, and it represents how quickly this system decays. So it is similar to a time constant. It's not the same thing, but it's very similar to a time constant. We can also introduce a second parameter, omega naught, which will be defined as 1 over LC square root. And this is what's known as the resonant frequency of the circuit, having a value, units of radians per second. So the resonant frequency of the circuit has multiple different interpretations. If we were looking at the impedance of an RLC network, the resonant frequency is the one where the impedance becomes purely real. If we were looking at a filter circuit, which I know you guys don't know about yet, but we'll talk about later, the resonant frequency is the frequency at which the filter hits its peak amplitude. Normally, when there's more than one person in the room, I would have a discussion about the Tacoma Narrows Bridge. Have you ever heard of the Tacoma Narrows Bridge? So the Tacoma Narrows Bridge was a bridge that was built, I think, in the 40s or 50s. And it effectively broke itself apart because the wind started blowing at the resonant frequency of the bridge, causing the oscillations to have their maximum possible amplitude, which was enough stress on the system to cause the bridge to completely and utterly collapse. Brand new bridge, huge project. In the 40s or 50s or whenever it was built, it was literally billions of dollars thrown away over the 2 months or something like that. That's how new the bridge was when it completely collapsed. And it was because they didn't take into consideration the wind load and the oscillations that would cause. When the wind blew at a very specific speed, it caused oscillations at a very specific frequency, which happened to be the resonant frequency of the structure, which caused the whole thing to collapse. If you're ever at a construction site and you see people loading stuff on scaffolding, they'll often walk by and hit the scaffolding with a wrench. If it makes a high pitch sound, you're good, but the lower in pitch that gets, the closer you are to having that system collapse because the resonant frequency is getting closer and closer to DC steady state, meaning the whole thing is going to fall apart. So that's some mechanical engineering interpretation of resonant frequency. For us, it really just means, well, it's really just a parameter that we're going to be solving for and doing some comparison with. So with that in mind, I can re-express S1 as negative alpha plus the square root of alpha squared minus omega naught squared, and I could say that S2 is negative alpha minus the square root of alpha squared minus omega naught squared. So this is my second solution for that second order polynomial. So in general, I can see a couple of different things by looking at the values of alpha and omega naught. All right, so let's look at situation number one. So let's say that alpha is greater than omega naught. When alpha is greater than omega naught, S1 and S2 are real and negative. And our voltage, in this case, V of t, will then be of the form A1 e to the S1t plus A2 e to the S2t. I have two different frequencies which cause this guy to decay to zero, and so I have to have two different coefficients to account for that. So effectively, one of the coefficients is due to the initial condition on the current flowing through the inductor, and the other is due to the initial voltage across the capacitor. All right, so I have two energy storage elements, each having two initial conditions, and those initial conditions show up as coefficients A1 and A2, or they're related to coefficients A1 and A2. All right, this system is what's called an overdamped system. In an overdamped system, the voltage, current, etc., will decay to its final value, typically 0, unless we have some excitation function in there, over a long period of time. So it reaches it very, very slowly. Situation number 2. Yeah. Capacitor, yes. So we are going to solve a problem, and it'll be a little bit more obvious how we determine those coefficients. If S1 and S2, or excuse me, if alpha is equal to omega naught, then this means that S1 and S2 are negative and equal. Okay. So if S1 and S2 are equal to each other, it may seem that we could just have a solution that was A1 e to the ST plus A2 e to the ST, if we looked at our previous our previous response equation, right? However, that would just combine together to make one single expression. But we are going to have two initial conditions that we have to deal with. So instead, we'll see that our voltage response equation, V of t, will be of the form A1 t e to the minus alpha t, because S is equal to negative alpha here, plus A2 e to the negative alpha t. So we have this first term that's being multiplied by time, and that's what's giving us the ability to take into account two specific initial conditions. I know that I in no way, shape, or form derived this equation. Short answer is I don't remember how off the top of my head. The long answer is this is how, when you have a repeated root for your eigenvalues, how it behaves, and you'll learn all about this in Math 245. So we're just going to take those results and kind of run with it. This system is called a critically damped system. And so in a critically damped system, the response decays to its final value in the shortest amount of time possible without having any overshoot. And I know that you don't know what overshoot means, but I'll tell you about it when we talk about situation number 3, and then we'll compare all three of these guys. So in situation number 3, alpha is less than omega naught. And that's going to mean that S1 and S2 are complex conjugates of each other, right? If we look up here, we will, if alpha is less than omega naught, then we're going to have some real part plus some square root of a negative number, which gives us an imaginary part, right? So we're going to have the same real part, and then the imaginary part is going to have opposite signs, giving us complex conjugates. Skipping the ugly math, our response equation then becomes B1 cosine omega dt plus B2 sine omega dt, all of this multiplied by e to the negative alpha t, where omega d, which is called the natural resonant frequency, is given by the square root of omega naught squared minus alpha squared, and is measured in radians per second. A system in which alpha is less than omega naught is what is known as underdamped. And so it hits its final value very rapidly, but then it rings. So I'm going to draw probably a terrible graph, but it'll be okay. This is time. And this is voltage in this particular instance. So let's say that this blue curve represents a overdamped system. So our response might look something like this. We start with some initial value. We decay, actually, I don't want to ring. Decay very slowly until we hit 0. Red will be for critically damped. So we'll start with the same initial condition, but we'll get to 0 much faster. Green will be for underdamped. Start with the same initial condition. And we're going to overshoot and oscillate several times before we finally settle to our final value for the system. So before we move along to our example problem here, I want to go all the way back to the beginning and ask you a question. What if this switch went in the opposite direction? What if our system started with no energy and then we forced a forcing function like this current source on it? We're going to have almost an identical response, but instead of everything decaying to 0 as time progresses, because all of the energy is being converted into heat by the resistor, we're going to have the opposite effect, right? So all of the energy is going to wind up stored in the inductor. So we can actually model that behavior doing the exact same derivation that we had there for everything, except now we're going to make one small change to our 3 situational response equations. Plus V at infinity, plus V at infinity, and plus V at infinity. That's it. So we now know that our system will have some finite value for our response as time progresses because we forced it to. That's what a forcing function does. All right, so I have created a table of parallel and series RLC responses, okay? Where I've just effectively summarized all the stuff that we just developed. But I've also provided you not only with the response equation. So for instance, at the very top on the right hand, the rightmost column, I have y of t is equal to a1 e to the s1t plus a2 e to the s2t plus y is at infinity, which is the exact equation that we came up with the derivation and all that kind of good stuff. But y of t could be a voltage or a current. And so I know that we explicitly derived everything here having to do with really the voltage drop across the capacitor. But Kirchhoff's voltage law and Kirchhoff's current law are going to force all voltages and all currents to be of that exact same mathematical type. So they're all going to look like a sum of exponentially decaying functions. Underneath that y of t expression, there's an expression for the derivative. So I have taken the time to calculate the derivative of all of my response functions because I know that the current and voltage in an inductor have a derivative-based relationship between the two, and the current and voltage in a capacitor have a derivative-based relationship. And we're going to have to use those derivative-based relationships to use our initial conditions on our system. So most of the legwork is already done for you in all of these. We're just going to be referring to the table as necessary. So now I'd like to take the time to outline how we should go about solving a problem by solving a problem and going through it step by step. And if you've looked at the homework sets, this is the exact order that I ask you to do the problems in. It will be the exact same thing on your test. Effectively, if you do these steps in this order and you do what trivial amount of circuit analysis is necessary, you will get all of these right every single time, and I'll show you how to verify it using LT-SPICE as well. So, with that being said, let's work an example problem. Probably only have time for one. So I'm going to start with the following circuit. I have an 8-volt source in series with a 20-ohm resistor. I have a switch that is closing at t is equal to 0. Five-ohm resistor. Sorry, that should be an inductor. A 2-Henry inductor. A 0.5 farad capacitor. And then way over here on the right, I'm going to have a current source supplying 1 amp. And all this stuff is connected down here at the bottom. So, Ms. Broussard, because you're the only person here, I would like for you to tell me 2 quantities that you would like to solve for the RLC network. So resistor current or voltage, capacitor current or voltage, inductor current or voltage. Any 2 of those 6 quantities we can solve for. All right, so the current through the inductor. All right, and the voltage drop across the capacitor. I'm going to call that V of t because it's also the voltage drop across the inductor and also the resistor. While I'm at it, so I'm going to put this in blue, we are also going to have to take into account Well, actually, that's not entirely true. But it isn't going to hurt us to take into account the current flowing through the capacitor as well. We do not need to keep track of the current flowing through the resistor. And I say that because once we know the voltage drop, we can just divide it by 5 ohms and then we have the current flowing through it. So typically speaking, the resistor quantities are the things that are found last after you've found either the capacitor voltage or the inductor current. All right. So step number 1. We want to determine alpha and omega naught during the transient condition, okay? So what we're trying to do here is to find the equivalent resistance, equivalent inductance, and equivalent capacitance of this network after the switch has closed, okay? Because we're going to find these directly, I'm going to look at a dead network, right? So I'm finding the Thevenin equivalent resistance, the Thevenin equivalent inductance, and the Thevenin equivalent capacitance. Well, let's start with something real simple, right? So with my dead network, where my voltage source is turned off, I'm going to have something that looks like this. Where my current source was. So effectively what I'm doing here, if I want the Thevenin equivalent resistance, I take my inductor and capacitor out and look in through that set of terminals to see what's left. So if my inductor and my capacitor were an open circuit, what would I see? Exactly right. So we can say that REQ is 20 ohms times 5 ohms divided by 20 ohms plus 5 ohms is 4 ohms. I only have one inductor, so I would argue that the equivalent inductance is going to be pretty easy to figure out. It's going to be 2 henries because it can't be anything else unless the inductor were shorted out, and it is not. Similarly, I could say that my equivalent capacitance, CEQ, is simply 0.5 farads. Allergies driving me nuts today. So from these quantities, alpha is going to be 1 over twice REQ times CEQ, which is going to be 2 times 4 ohms times 0.5 farads here, is going to be 0.25 amperes per second. It's just 1 over 4. And omega naught will be the square root of 1 over LEQ times CEQ, which is going to be, let's see, 2 henries times half a farad to the negative 1/2 power, which is 1 radian per second. So now I can compare alpha and omega naught and see whether my system is critically damped, overdamped, or underdamped, which will let me know which response relationship to use. So omega naught is obviously larger than alpha, which means that this circuit is underdamped. So omega naught larger than alpha, we have an underdamped system. So that is step one. We calculate alpha, calculate omega naught, and determine whether the system is critically damped, overdamped, or underdamped. Step number two, we will analyze the circuit at t is equal to 0 minus. Circuit at t is equal to 0 minus. So at t is equal to 0 minus, this is before our switch has changed states. So it is before the transient conditions occurred, meaning that our circuit is at DC steady state. So we can replace all of our inductors with short circuits and all of our capacitors with open circuits. Also, because it's before the switch has changed states, it was open and then it closes at t is equal to 0, we're going to replace our switch with an open circuit in this particular example. So that's going to look like this. 8 volts, 20 ohm resistor, open circuit here. Here is our 5 ohm resistor. Here is our inductor. This is what our capacitor looks like. And then out here is our 1 amp current source. So, of interest is going to be the voltage here at t is equal to 0 minus, our inductor current through this short at t is equal to 0 minus, and we are going to keep track of this capacitor current at t is equal to 0 minus as well. So, Broussard, I'm going to continue to pick on you because you're the only person that physically shows up to class most days. Hope that's okay. I believe that we can determine all three of these quantities by inspection. So, what do you think the voltage drop should be? 0 volts. You're correct, but could you explain yourself?
Well, there's no voltage drop across the resistor because all of the current would be flowing through the short circuit where the inductor is.
Absolutely right. So another way of stating that would be the capacitor is in parallel with the inductor, which looks like a short circuit. So the voltage drop over the short circuit is 0. Therefore, the voltage drop over the capacitor has to be 0. But your way of looking at it from no current flowing through the resistor, meaning no voltage drop across the resistor, is perfectly correct as well. What about my inductor current? What is that going to be? 1 amp, for the reason you previously stated, right? All of the current's going to flow through the short circuit. Lastly, I have my capacitor current. What is that going to be? 0 amps, because no current can flow through an open circuit. So, gosh, my nose is itching like crazy. So we have successfully analyzed the circuit at t is equal to 0 minus. We have our three quantities of interest. So let's move along to step 3. So at step 3, we are going to analyze the circuit at t is equal to 0 plus. So at t is equal to 0 plus, the circuit is no longer at DC steady state, And also, I want to take note that the switch is now closed. So I have my 8-volt source, my 20 ohm resistor, my switch is closed, so now there's a connection between the 20 ohm resistor and my RLC network, right? So I'm going to draw my inductor here, which is 2 henries, my capacitor here, which is half a farad, and then my 1 amp source. So let's talk about a couple of things here, right? The first of which is that we know that capacitor voltages cannot change abruptly, because doing so would cause an infinite amount of energy transfer in an infinitesimal amount of time. So the voltage drop across our capacitor, 0 volts. We know that has to be true. If it was 0 volts at t is equal to 0 minus, it has to continue being 0 volts at t is equal to 0 plus. Similarly, the current flowing through an inductor cannot change abruptly. So if it was 1 amp flowing down at t is equal to 0 minus, it must continue to be 1 amp flowing down at t is equal to 0 plus. I like to represent this by changing my capacitors into voltage sources and my currents into current sources, because that is exactly how they were behaving at this particular instant in time. They have a fixed amount of voltage. Excuse me, my capacitor has a fixed voltage, and it doesn't matter how much current flows through it. Similarly, my inductor has a fixed amount of current, and the voltage drop over it is inconsequential. So I'm going to replace my inductor with a 1 amp current source. I'm going to replace my capacitor with a 0 volt voltage source, which is just a short circuit. And so this is effectively what my system looks like. And the only thing I don't know is my inductor current at t is equal to 0 plus. So to reiterate, go away. V at 0 plus has to be 0 volts, because the voltage drop over my capacitor cannot change abruptly. IL at 0 plus has to be 1 amp, because the current flowing through my inductor cannot change abruptly. And so now I need to figure out what IC is at t is equal to 0 plus. Any thoughts?
Would the voltage across the 5 ohm resistors also still be 0 since they're in parallel?
Yes, so the voltage drop across the 5 ohm resistor is absolutely still 0, because it's in parallel with the short circuit that is representing the capacitor right now.
Can we use nodal analysis at the top of that?
We could, but I believe that to be overkill. Let me explain why. I have a 1 amp current source flowing down that is representing my inductor, correct? And I have a 1 amp current source flowing up that is representing my independent current source. Those two current sources are in parallel. So what happens when I have two current sources in parallel? Well, I can combine them, and they're going to combine to be a 0 amp current source, right? So I could just as easily say that I have an open circuit here and an open circuit here. Does that change the type of analysis you would like to do?
It would be the current going through the 20 ohm resistor then.
Exactly right, which is just given by 8 volts divided by 20 ohms is 0.4 amps. Goodness gracious. All right, so we now have our three quantities of interest at t is equal to 0 plus. Step 4 is analyze the circuit at t is equal to infinity. At t is equal to infinity, the circuit is at DC steady state again because it's a long time after the transient condition has decayed. And the switch is still closed, right? So that means that I'm going to have the switch closed, but with my inductors replaced with short circuits and capacitors replaced with open circuits. So that's going to look like this. So let's see, here's my 20 ohm resistor, 5 ohm resistor, my inductor is a short, my capacitor is an open, and then out here, I have my 1 amp source. This is my voltage, V at infinity. Here's my inductor current, IL at infinity. Here's my capacitor current, IC at infinity. So, Ms. Broussard, what is my voltage at t is equal to infinity? 0 volts. All right. What is my inductor current at t is equal to infinity? Right, so there's going to be a contribution of 1 amps coming from the right and a contribution of 8 volts over 20 ohms coming from the left, giving me a total current of 1.4 amps. Lastly, my capacitor current is going to be 0, because no current can flow through the open circuit. So we have completed our circuit analysis at t is equal to infinity. Now we are finally at step 5, where we use the table. Step number 5, use the table to calculate the quantities of interest. All right. So because our system is overdamped, I can say that my inductor current, IL of t, excuse me, it's underdamped. I can use my table to say that the inductor current, IL of t, will be of the form B1 cosine omega dt plus B2 sine omega dt multiplied by e to the minus alpha t plus IL at infinity. So as a quick aside, we see that omega d has popped up in here a couple of times, so now is as good a time as any to calculate it. Omega d is going to be equal to the square root of omega naught, which was 1 radian per second squared, minus alpha, which was 0.25 nepers per second quantity squared. And so if I do that math, I get 0.968 radians per second. All right. So coming back around to the problem at hand, I know what's going on at t is equal to 0 minus and t is equal to 0 plus. I have a really good grasp on that. I also know what's going on at t is equal to infinity. So what I'm going to do here is I'm going to say that IL t is equal to 0 plus is going to equal something here. So I'm just going to substitute in t is equal to 0 in my equation, right? So what is the cosine of 0? All right, so that means I'm going to have b1 times 1 plus b2. What is the sine of 0? E to the 0 is what? All right, so all of that multiple, thank you, all that's multiplied by 1, and then plus IL at infinity, which we found to be 1.4 amps. So actually, let me write that. IL at infinity. So substituting in numbers here, I can say that IL at 0 plus, which we knew to be 1 amp, if I'm not mistaken, yes. 1 amp is equal to B1 plus 1.4 amps, which tells us that our first coefficient, B1, is negative 0.4 amperes, right? So we've got one of our two coefficients already taken care of, related to our initial conditions on our inductor current, and also had something to do with the final condition because this guy had a non-zero infinity value. The next thing that we're going to do is look at our derivative-based relationship, right? So if I have the inductor current, then I'm going to now look at the inductor voltage. E of t, which is equal to L times the derivative, where I'm not going to take the derivative of this big ugly thing. That's what the table is for, right? So if I look at my table and I go down to the dy by dt for underdamped systems, I know that this is going to be omega d b2 minus alpha b1 times the cosine of omega dt minus omega d b1 plus alpha b2 times the sine of omega dt. Goodness gracious. E to the minus alpha t. Voltage at 0 plus is then going to simplify to what, right? So we're going to have L times omega d b2 minus alpha b1. And that's it, because we know that cosine of 0 goes to 1, sine of 0 goes to 0, and e to the 0 goes to 1. So from this, we can say that 0 volts, which was V at 0 plus, is equal to 2 henries times omega d 0.968 radians per second times B2, which we don't yet know, minus alpha 0.25 nepers per second times B1, which we found to be negative 0.4 amps. And we can solve this one equation, one unknown, and get a value for B2. So I find that B2 is equal to negative 0.103 amperes. All right. So from here, it's just substituting things back in. Now that we know what B1 and B2 are, we can actually solve for everything, right? So what I mean by that is my inductor current, IL of T, and this equation will be valid for all T greater than 0 plus, is simply B1 0.4 cosine omega D, so 0.968 T, plus B2, so I'm going to have plus 0.103 sine omega dt, 0.968 T. Close this guy e to the negative alpha, so negative 0.25 T plus 1.4 amps. So I literally just substituted B1 omega D, B2 omega D, and alpha and I at infinity into my response equation. I don't have to do any more work whatsoever. For V of T, I'll have to do a little bit of work. But it's just going to be simple multiplication of things, right? Because if I look at this equation up here that I used, I know L, I know omega D, I know B2, I know alpha, B1, etc. I know all of those different things, so now I just have to multiply those things together. What I'm going to wind up getting is 0 cosine 0.968 T. I could just have easily just not included that part, but I want to show you that it will be of the exact same form, plus 0.826 sine 0.968 T e to the minus 0.25 T volts. All right, so we'll give you a minute to finish writing that down, and then we are going to spend the next 5 minutes or so looking at LT Spice and seeing how we can verify these things. So I have drawn our circuit during the transient condition, right? So this is effectively what it looks like at exactly T is equal to 0 plus, where I have specified that I have an initial condition on my capacitor voltage of 0 volts, which I did with our dot IC V open parentheses VC is equal to 0. And I also say that I have an initial condition on my capacitor, excuse me, on my inductor current of 1 amp. So one thing that I want to point out here, I always choose my ground to be the negative polarity terminal of my capacitor voltage. Because if I don't do that, and I try to put an initial condition on my capacitor voltage, it's either not going to be correct, or I'm going to have to do a larger mathematical expression where it's the voltage present at the positive polarity terminal minus the nodal voltage present at the negative polarity terminal. It's very, very easy to make a mistake there. So I always arbitrarily choose ground to be the negative polarity terminal for my capacitor so that I cannot make a mistake. All right, I have set this guy up to run for 25 seconds. I chose that value because I know that this thing is decaying at a rate, or its alpha value is 0.25. So that means roughly every 4 seconds. Like if I were treating it as a time constant, that would mean that I have a time constant of 4 seconds. And so I'm doing it for over 5 time constants to make sure that it fully decays. So if I run this simulation, it's being difficult. Get my mouse going. I run the simulation, make this fit. So let's look at our capacitor voltage first. So it looks like it's an underdamped system because I do see that oscillation. If I right click on my graph and add a trace, what I can do is type in the mathematical expression. So I'm not going to do the 0 times cosine because that's pointless. 0.826 times the sine of 0.968. And I'm about to do something here that is critically important. If you don't do this, your answers are always going to look like they're wrong. LT Spice does everything in degrees. Omega D, by definition, is radians per second. So we need to convert it to degrees per second. So I'm going to multiply by 180 and divide by pi. If I do not do that, my analytical solution will not match the simulation. Now I multiply omega D times time, close parentheses, multiply by the exponential of negative 0.25 times time, close parentheses. The blue curve completely overlaps the green curve, which means our analytical solution exactly matches that of the simulation. So we are correct. I can also verify my expression for the capacitor current, or excuse me, my inductor current, right? So if I click over the middle of the inductor, I get my current probe. Now let's put in that expression. So add trace. And so I have, let's see, negative 0.4 times cosine 0.968 times 180 over pi times time plus 0.103 times sine 0.968 times 180 over pi times time multiplied by exp negative 0.25 times time, close parentheses. Oh, and I almost forgot, plus 1.4. And again, the blue curve completely matches the green curve. And also notice here that my scale on the left-hand side exactly matches the scale on the right-hand side. It is possible to get the correct answer, but if the scale on the right-hand side doesn't match the scale on the left-hand side, it's going to look like it's wrong. So always make sure that they match. So we have analyzed the circuit perfectly. Those 5 steps are all you do for any of the different configurations that you can have. Doesn't matter whether it's overdamped, critically damped, underdamped, those 5 steps work every single time. I will say one mistake that I see students make, my derivative-based relationships, so where I have dy by dt, does not include the capacitance or the inductance, right? But I know that, so like the derivative, excuse me, the voltage across an inductor is L times the derivative of the current, or the current through a capacitor is C times the derivative of the voltage. If you don't remember to multiply by L and C as appropriate, then you're obviously not going to get the right answer. There is nothing preventing you from using integral-based relationships either. You will get the correct answer, but in my opinion, it makes the math more difficult, and so I avoid them like the plague and just use these integral-based relationships. So let's revisit our problem just real quick like, all right? Don't have much time, so I'm not going to go through anything in particular, but if we were interested in finding the capacitor current from here. Any thoughts on what we could do?
If we would have the same, like, the one, but we would have to solve for different.
Right, so it's going to be of this same form for sure, but we would have to solve for a different B1 and B2. But we know, for instance, that IC of T will be C dV by dt. Well, we already know what V is, so we could now use that. Another way would be, we know what VT is, and then and so we could effectively start this entire problem over, but start with our capacitor voltage as our thing that's telling us what coefficient B1 is, and then use the derivative base relationship given by here as the second equation, which gives us our coefficient B1. So we could do the exact same thing, but we would put VC here and then IC there. And then we'd get our coefficients. We can never do this with resistors because the current and voltage drop across a resistor does not have a derivative-based relationship to be able to use. So for a resistor, we always have to solve for one of those capacitor or current, inductor quantities, and then figure out what's going on with the resistor after the fact, which in this case would just be V divided by 5 ohms if we wanted this current, or it would be 8 minus V over 20 ohms if we wanted this current. So we have enough information to figure out what's going on with the resistor after we've solved for, in this case, the voltage. With the inductor current, by itself, we would need to do a little bit more work. So in your homework problems and stuff like that, like you'll have to rely on Kirchhoff's current law and Kirchhoff's voltage law based relationships usually to find out what's going on with the resistors. And if you have any questions about the homeworks, I'd be happy to answer. All right, so I think that's enough out of me for today. So what we're going to do on Tuesday or tomorrow is go through a similar derivation and an example problem for series RLC circuits. And then on Thursday, we're going to break everything by making our system not series and not parallel, and then see how to deal with that. That's the general case. And we're going to spend 2 days on that just because the math is, it's super tedious, but not hard. It's just literally tedious and takes a while. And then we're finished with transient analysis and we'll be ready for exam 1, which I think will be next Tuesday. Yeah. So exam 1 will be next Tuesday. It will cover all of the material for op amps and all of the transient analysis material. That being said, the in-class portion will only have what we're covering today and tomorrow. The take-home portion will do the general RLC, because if I asked you to do a general RLC problem in an hour and 15 minutes, you might not be able to do it just because the math is so tedious. Not remotely difficult, just wildly tedious. So. Alrighty, so I will see you guys tomorrow morning.